physical oceanographer. What this means is that I study the way that the ocean moves. I study the mechanics of the ocean. I don't study the plants or animals that live in the sea, but rather the forces that set the background environment in which those plants and animals live. And today I'm going to be talking to you about oceanography and specifically the Weddell Sea. So to start off, this is a map of ocean sea surface temperature taken from satellites. The reds show a warm ocean. Wrong button. There we go. The reds show a warm ocean and the blues show a cold ocean. Now, why are the equatorial oceans warmer than the polar oceans? Well, if we took an imaginary sun, which is over here, and we took an imaginary ray of sunshine from the sun, and we shone it at the equator, and then we shone the same ray of sunshine at the poles, you would see that the area of Earth's surface that is heated up by that ray of sunshine is much smaller at the equator than at the poles. So the equatorial oceans receive more direct, more intense sunlight, and so they are warmer. Now, why does the equatorial ocean not just continuously heat up if it's receiving this increased solar radiation? Well, because we have ocean currents that transport these warm equatorial waters polewards. So this is a map showing sea surface currents, also from satellite data, and the greens and yellows show fast-flowing currents, very rapid-moving oceans. So, for example, in the North Atlantic, we can see over here the Gulf Stream, which transports warm equatorial waters northwards, just off our coast here, off of Manhattan. Now let's take this picture and let's flip the globe so that we're looking from the perspective of the South Pole. So here we have Antarctica, South America, South Africa, where I'm from, Australia, and once again, the yellows and the greens show these rapidly moving ocean currents. So over here, this is the Agulhas Current, which transports warm equatorial Indian Ocean waters towards the Southern Ocean. This is the Southern Ocean. And when these warm equatorial waters reach the Southern Ocean, they get entrained in what is known as the Antarctic Circumpolar Current, which is this series of squiggles over here. The Antarctic Circumpolar Current is the longest and strongest current in the world. It is set up by the westerly winds, which blow over the ocean and set the ocean in movement. And because there are no land barriers, this ocean current is able to circumnavigate our planet, connecting the three major ocean basins, the Atlantic, the Indian, and the Pacific. Now, why does the ACC, the Antarctic Circumpolar Current, not just continuously grow in mass and volume if it's being fed by these currents transporting warm equatorial waters polewards? Well, because of something called bottom water formation. Bottom water formation is when you take surface water and you convert it to water that lives at the bottom of the sea. And the Weddell Sea is one of the key formation sites, one of the 4 main formation sites in the world for this bottom water formation process, which we'll get to. So you'll notice now on this map of satellite data that the Weddell Sea is actually black. There's no data. And that's because this area is covered in ice. So satellites can't actually see the surface of the ocean, which means we have to go there in person to get data on that area. So let's take the same view from a polar view of the world. And now let's look at these different currents at different depths. Now I know it's confusing to think the ocean is moving in different directions at different depths, but that's exactly what it does. So what is shown here is something that is known as the global ocean conveyor belt. It's a series of currents around the world that transport heat and salt and many other properties, just like a conveyor belt at the airport conveys your suitcases around. The global ocean conveyor belt does the same thing. So the red lines show surface currents, warmer currents, and the blue lines show deep currents, currents that flow along the ocean floor. And you can see here in the Weddell Sea, there's a conversion between surface current and deep current. And that is that process called bottom water formation. So how does this work? Well, in wintertime in Antarctica, you have very cold winds that blow off the Antarctic continent and over the ocean. And they super cool the surface of the ocean to the freezing point of seawater. What then happens is you have sea ice that forms. Now ice is fresh. So as sea ice forms, you have brine rejection of salt crystals from the ice into the surface of the ocean. The surface of the ocean is then very cold, temperature drops, and super salty because of that brine rejection. Super cold, super salty water is dense, which means it's heavy. This water literally sinks from the surface of the ocean all the way down to the ocean floor. And as it sinks, it carries with it carbon, oxygen, and nutrients. It takes nutrients out of the photic zone, the light zone, where phytoplankton, little ocean grass, can use those nutrients. It takes them down to the bottom of the ocean. This bottom water then spreads out around our planet, carrying all of those signals, the carbon, the oxygen, the nutrients, and then eventually upwells in equatorial and tropical oceans around the world. And when those nutrients are brought back up to the surface, they can then be used by phytoplankton in those areas. So, in fact, 70% of global ocean primary productivity outside of the Southern Ocean, so outside of this area, is sustained and controlled by the Southern Ocean. So these processes that are happening in Antarctica and specifically happening in the Weddell Sea are important for climate regulation, for ocean circulation, but also for ecosystems around the world. So we went over here, the Weddell Sea, so let's zoom into that area. And once again, this pink line was that surface current of that global ocean conveyor belt. Here we have the Antarctic Peninsula, we have Larsen Sea ice shelf, the Filchner-Ronne ice shelf, and these blue arrows show that process of bottom water formation, that very dense water sinking. It sinks down over the continental shelf, down the continental slope. The background shading is ocean depth. And then these white lines show how that dense bottom water then spreads outside of the Weddell Sea, joins the Antarctic circumpolar current, and spreads into the major global ocean basins. Cool. These red dots over here show where we went, where we took oceanographic measurements. And you can see they're clustered around that northern part of Larsen Sea ice shelf. And this is an inset of that area. And you can see we focused our efforts between Larsen Sea, that massive iceberg, A68, like John said, 100 times the size of Manhattan. A68 broke off of Larsen Sea in July last year. This constituted a 12% loss of mass for Larsen Sea ice shelf. Now in 1995, we lost Larsen A ice shelf. Larsen B ice shelf began its demise in 2002, and by next year, Larsen B will be gone. So massive calving events like this are of interest, but also of concern to the general public, but to oceanographers and cryosphere scientists. So that's why we decided to focus our efforts on this area, and let's see how we did that. What did we do, and how did we measure? So this is the SA Agulhas 2, the South African research ship, which John showed you. There's a little door that opens up in the side of the ship, and we deployed something called the CTV. CTV stands for conductivity, which is a proxy for salinity, temperature, and depth, because it measures those things amongst many other things. So it's deployed out of the side of the ship, and it gives us measurements like this. So this is a profile of salinity, temperature, and oxygen over the top 500 meters of the water column. This can go all the way down to the ocean floor, down to 5,500 meters. But we were on the continental shelf next to Larsen Sea, so we were on average about 500 meters deep. And you can see, for example, for temperature below the surface, all the values are below -1 degree Celsius. That's below 30 degrees Fahrenheit. So really cold, super salty water. And this is our team of South African oceanographers, which literally drive the winch, so lower this instrument through the water column and get a live feed of the oceanographic data. So why? Why did we go and spend all this time, energy, effort, money going to one of the most remote places on Earth to get oceanographic data? Well, because this picture is changing. Through our production of greenhouse gases, we're intensifying the effect of sun's radiation on the Earth's surface. We're trapping the solar radiation. And as a result, the ocean heat content is increasing. So the oceans are absorbing the increased heat in the atmosphere. So this is a graph showing ocean heat content over the last 140 years. It's for the surface ocean, but the trends are the same all the way down to the depths of the ocean. And you can see that in the last 50 years, there is an increase in ocean heat content. These different lines represent different estimates, some from models, some from observations, some from models that simulate observations, and you can see they all agree. So it's a pretty robust trend that the ocean is warming. Now, what does this mean? Well, a warmer ocean takes up more space because of something called thermospheric expansion. So warmer water literally expands. So in the last 50 years, we've had about 0.5 meter sea level rise just because the oceans have warmed, not because of any ice caps melting, just the thermospheric expansion of the ocean. And as the oceans continue to warm, they will continue to expand. The second thing is that ecosystems are adapted to their environments. And as we warm the oceans, those species are challenged. They either have to adapt or they die. The third thing is that a warm ocean can hold less gas. Warm water can hold less gas. So at the moment, the oceans are taking up 25% of the CO2 that we put in the atmosphere. Another 25% is taken up by plants and trees, and half remains in the atmosphere. But as the ocean warms, its ability to mitigate our production of carbon dioxide, to mitigate the effects of climate change, will decrease because it can no longer take up as much CO2. So how does this relate back to the Weddell Sea? Well, first of all, we want to understand what are the current conditions in the Weddell Sea, because in that area there have only been 5 oceanographic cruises in our history. So any data is extremely valuable to set a baseline from which we can then answer the second question, which is how much is the Weddell Sea warming? Which then will inform the last question, which is how much is the Weddell Sea warming and what is the effect on Larsen C ice shelf? Is there basal melting? Is there melting at the bottom of Larsen C ice shelf, which is destabilizing the ice shelf and causing these massive calving events? If Larsen C is melting, what is the effect on the land-based ice, on the increased flow to the ocean, which would cause sea level rise? And if the ocean is warming and we're having ice melt, that means its density is decreasing. So remember, cold, salty water is heavy, warm, fresh water is light. So what will the effect be on that bottom water formation, that vital limb of that global ocean conveyor belt that transports heat, salt, carbon dioxide, oxygen, nutrients around our planet? So, as humanity, we have some challenges ahead of us. And as scientists, there are still many questions that remain unanswered. But in the words of the great Sir Ernest Shackleton, difficulties are just things to overcome. So thank you for listening.